All right, in this video, I'm going to cover the difference between AC and DC coupling of the input probes. So you can see I have channel 1 turned on, and what I'm referring to is over here, this soft button. There's DC, AC, and ground coupling. So one of the things that you want to keep in mind is that electrical signals can have one of two components or both, those components being AC and the other components being DC. That's going to be an alternating voltage signal or a constant steady state voltage. Now there can be different combinations. It can be, for example, you can have a purely alternating sine wave, which, think of like the house current. Now that's going to be something, as you can see on channel 1 here, the yellow channel, it's going to be centered around 0 volts. It's going to be symmetrical. So you're going to have like your peak-to-peak voltage here is 4.08 volts. And it's going to be half on the positive and half negative. They're also going to have DC, which is nice, steady, linear, constant voltage. You think of something like a linear voltage regulator, like the classic 7805 will have a nice, steady, a straight line at 5 volts. You can also have AC, so you have primarily AC with a bit of a DC offset. You can think of amplifiers, or like I'm going to show here in just a minute, the clamping circuit. So you can see let me get that off. You can see the output voltage of the clamping circuit has a DC offset voltage to it. But then you can also have a steady state DC with a small AC ripple voltage riding on top of it. Think of something like a switching voltage regulator, or the ripple voltage off a capacitor on the output stage of a full wave bridge rectifier. Now in this example, you can see I've got just a really simple clamping circuit. So I've got my function generator connected to the terminals here, and it's just going through the breadboard. It's relatively low frequency, so this isn't going to cause a problem. So we've got the positive side of the voltage source on this side of the capacitor. Then we've got the clamping diode. This is just a 4148, and the cathode is pointing to ground. This isn't going to be a tutorial on how the clamping circuit works, but essentially it clamps the output to 0 volts, and depending on how the diode is biased, it'll either push the AC signal on the positive side of the 0 voltage, so you'll have basically a fluctuating positive DC signal, or it'll push it to the negative side of 0 volts, so you'll have a negative alternating DC voltage. All right, to get to the coupling menu, all you have to do is press the channel 1 menu selection. Now this brings up the soft menu, so the coupling selection is going to be over on this side with this oscilloscope. Now what coupling refers to is what of the two components of the electrical signal do you want to measure. Now when you're set to DC, it will measure both the AC and the DC, so it won't filter out any of the DC offset. Now if we're on AC, it will filter out the DC, and all we'll be left with is the actual changing voltage signal. So the input voltage right now is coming from the function generator. Now I don't have any DC offset, so there should be no difference between if I press the DC or AC coupling. So we're on DC right now. If I press this button again, it'll go to AC, and then you see that the signal doesn't change. And if I press the ground, then it just goes to flat. So the reason you would use this ground because you want to know where on your screen your zero or your ground references, or your 0 voltage references. And then once you turn it back on, you can know that this is actually 0 volts, this is your positive voltage, and this is your negative voltage. Now if I switch over to channel 2, so channel 2 is the output of the clamping circuit. So this is on between the capacitor and the diode. So right now I am measuring both the DC and the AC components of the signal. So this is the blue channel. Let me just get that off. And you can see that this is lower, but you can see by the labels that they're actually at the same reference point. So they're both, this is 0 voltage. Let me bring that back up. So if I switch it to AC, what will happen is that you'll see the waveform move up because I'm filtering out the DC voltage. Now there, this just confirms that your channel 1 and channel 2 are identical. which is what you want out of a clamping circuit. All it should do is either push the signal negative or positive. It's going to be clamped to the 0 voltage. Now, when you use DC versus AC coupling, all it has to do with what you're measuring. If the signal you're measuring is riding a DC voltage and that's important to your operation, then you'll probably want to measure both the DC and the AC components of the signal, which means it needs to be on DC coupling. Now, there will be certain times, where we'll see an example in a second, where let's say we're measuring primarily a DC steady state voltage, but we want to see the small ripple voltage. So then we'll actually use the AC coupling. All right, here I've built a simple full wave bridge rectifier. So we've got the AC voltage inputs in the top and bottom, then the DC voltage output across the resistor and the capacitor. So we've got the 4 diodes that are actually doing the rectification. They're doing the full wave rectification. So you've basically got like the 2 humps as opposed to the half wave, which you got a hump, then flat, hump, flat. This is a 100 microfarad capacitor. This is just 1K. I just chose those arbitrarily to give me a halfway decent amount of ripple voltage that we'll see. And so the circuit schematic is fairly straightforward. So this is the 2 inputs for the AC, and this is the ground output and the positive voltage for the DC output. This is the output capacitor, and this is the load resistor. Yeah, so this is 1K and this is 100 microfarads. All right, so if we look over here at the oscilloscope, I've got channel 1 is measuring the output voltage. I have it set to DC voltage. So I want to know what the DC level output is, and I also want to be able to measure I also want to be able to see the AC waveform of the ripple voltage. Now, one of the challenges is that in this kind of circuit, you want to be able to measure how much ripple voltage. So you can go with the cursors and you can try to measure the delta V, but that's not exactly going to give you a high level of precision. So one of the ways, so let's just turn those cursors off. So you can try to make this a little bit larger. So I'm at 5 volts per division. Maybe I can make that 2 volts per division. Then I can bring this down so I can measure it. So now I have a little bit more information. I can take the cursors and get a little bit more precise. So now, before it was 1 volt measured, now it's 640 millivolts. So it's a little bit more accurate, but still, this isn't even a full division. So now we can try to increase that again, go to 1 volt per division. Now the level is off the scale. I can try to bring that down all the way, and since it's basically an 8 volt DC, I can't bring it down anymore. So this is where and we just recenter this and change that to 5. So this would be a good case in where you don't want the coupling to be both DC and AC. So in this case, since I want to measure the amount of ripple voltage on that, I want just the AC. So I want to filter out the DC level. And you can see that brings it down to there is no DC offset. So now I can adjust the volts per division. So there's 2 volts per division, 1 volt per division, 500 millivolts. So I also want to change the scale a little bit, and change my trigger level so it's actually triggering. We'll do it right about there. So now we're at 200 millivolts per division and 4 milliseconds. So change that so it's nice in the center. So now I can take my cursors, I can use the multi-purpose knobs, and I can get a far more precise and far more accurate measurement of the amount of ripple voltage. So in the first instance, the voltage difference from cursor A to cursor B was 1 volt. Now, it wasn't nearly as precise. Now we're getting a lot more precise measurements, and we're actually just a little bit more than half that. So by by filtering out the DC and keeping the waveform centered around 0, I can change my vertical scale to a smaller value, so then I can actually measure much more accurately. So there is only one little gotcha about the DC and AC coupling. This has to do with low frequencies. So right now I've got a 250 hertz square wave. So the input is channel 1, and the output, this is the clamping circuit, is channel 2. So this just has a little bit of a DC offset. So we can see channel 1 is set at DC. So if I change it to AC, again, there's not much. As we get into lower frequencies, we'll see that this is interpreted as a constant steady state voltage, that if we're in AC coupling, it will distort the waveform. So let me drop that down. So I'm going to drop that down to 25 hertz and adjust my time scale. So I've changed nothing about it except the frequency, right? 25 hertz, you can see right there. But if I change it to DC coupling, it won't filter out the DC. So this is beginning, it's a low enough frequency that this is starting to behave like a steady state DC offset. So I change that to DC. Now it's not filtering out the DC component of the signal, and it's all nice and flat. So now if I decrease that even further to 2.5, let's get this. See, if I go to AC, you can see that the output is significantly distorted. So I'm going to just do a single capture of that and get rid of this. So now you can see there is just significant. Now we can see channel 1, we are at AC coupling. So we're filtering out the DC, and the result, since this is at 2.5 hertz, it's actually filtering out the information we want. So if I change this back to DC and hit run again, just kidding, you can see that it doesn't filter out the DC. So this is just something to keep in mind with the particular low frequency. Now obviously if I go back up to 250 hertz and adjust the time scale appropriately, everything's fine. So we can see we've got nice flat DC component to it. So I can even go to AC coupling and I don't get the same distortion. Even channel 2, I'm on DC because I want to show that DC offset. The only difference if I go to AC coupling is that it filters out the DC, but then it's just identical to the input channel, and it really makes no difference. It doesn't help me for this particular circuit. So that's just a little trap for young players on low frequency and AC coupling. All right, I hope you found this video helpful.